I've already updated the syllabus by including the TA information. We now have a TA information for this course, and I will advise that you check the syllabus for the information. Today, we're actually going to continue from the material that we started yesterday. Give me 1 second. Okay, as you can see what I'm projecting right now, this is where we stopped yesterday, and of course I promise actually going to continue from this. Yesterday I remember you were being introduced to a topic that we actually call the probability in a finite sample space. And of course, earlier I told you we find ourselves in a world that is stochastic in nature. We live in a probability space, and because of that, we actually need to acquire statistical knowledge to be able to, take a decision that we don't want to regret. Different things happens in this world. There's a lot of variations. We have actually seen experts, taking decision in the past and they regret that. And we have seen those who took a very good decision. And that is the reason why we actually need to understand our basic probability theory, provided, in statistical architecture, so that we'll better understand our environment. Okay, so like I said, today we actually going to continue from where we stopped. And of course, we are actually going to start from intervals. Just like what I told you yesterday, the way I learn my mathematics, the way I learn my statistics, I like relating to real life practical situation. Now, I want you to be picturing something in your mind now as to what the application of this is going to be. Now we're talking about intervals. Okay, we have a random variable x. We want to believe that a particular random variable x cannot just take all values in this world. There's always going to be something that we call a neighborhood. It's just like you have countries that have map, every country has their own territorial jurisdiction. Now, when you take a look at this guy now, okay, if we have something like this, where you have an open, at both ends, so mathematically speaking, what we mean is this. What we actually means, in each of these cases, we're taking values in real number. I introduced you to real numbers yesterday. Real numbers have all the numbers in this world, including all the integrals, the odd numbers, the natural numbers, and so on like that. So now if we are interested in S, we know that S actually come from real numbers, but at times we may not be interested in all of them. Probably we're interested in a particular values of S that actually greater than A, but less than B. That is what this guy means. Okay, it is greater than A or less than B. Okay, that is what that means. And that is basically open above hand. Okay, so if you take a look at the next one, I also wanted to pay attention to notation, the way the first one is written is quite different from the way this is written. You can see the kind of parentheses that we have right now is different from the first one. So this is actually close. Anytime you see something like this, okay, yeah, it's actually going to introduce equality. Okay, look at that. So that is equality that I actually talk about. So it's trying to say that X lie between A and B, inclusive. It's just like example I cited yesterday, there's a difference between this and this. If you look at this guy here, the one I circled, 1 and 6 are included. But when you look at this guy now, okay, the 1 and 6 are not included. I just wanted to take note of that. Okay, now we can also have situation where it can be open at one end and close at the other end. So situation of where it is open at A, of course, that is going to be strictly less than. And the close at B, then that's going to be less or equal. Take a look at that. Okay, so we can also have where it is close at A but open at B. So we're going to have this. And all we're just, with this, we are trying to pass information about what the interval of a particular random variable under investigation can be. The random variable S that I'm talking about could be blood pressure, okay? It could be price of stock, okay? It could be gas price, okay? It could be anything at all that is liable to change, okay? Don't forget I said we live in a stochastic world. Okay, now that is the types of intervals that we actually have, and there are 4 of them. But I wanted to take note of something. Anytime you see us writing something in this way, we are basically trying to say A is less than B. I can write 2, 4, okay? I can, this is not right, this is wrong. Why this is right? Okay, we have to go from the smaller number to the bigger number. We don't go from the bigger to the smaller number anytime we're dealing with the interval. I just wanted to take note of that. And that is the reason why we are actually saying A is basically going to be less than B, or A is going to be the lower bound and the B is going to be the upper bound. Okay, I need every one of you to confirm again if you are still hearing me clearly. Are you all still hearing me clearly?
Yeah.
Thank you so much. Oh, thank you for confirming that. Okay, so I want to go to more, the interval I showed you the other time is basically where you have the lower endpoint and the upper endpoint. So what if in a situation where you only have the lower endpoint and you don't have the upper endpoint, the upper endpoint is actually infinity, or we could have a situation where the lower endpoint is negative infinity and the upper endpoint is a particular value. That is exactly what we're trying to show here. Take a look at that guy now. We have a lower endpoint A and we have the upper endpoint infinity. And the way to write that is just to say A is less than X. Take a look at that. In that kind of situation, A is basically less than X. And don't forget our X lies a real number. And of course, we can also have, close at one hand, open at that hand. You can see the difference between the two, it's just like you are introducing equality sign here because of the fact that it is close right here. Okay, take a look at that. And what if in a situation where I want to go from negative infinity to a particular point, and you know what, they are both open at both ends. Of course, this is how we're gonna write that. Okay, take a look at that. And what if in a situation where it is close at the other hand, you're basically gonna introduce equality. And what if in a situation where we actually want to use all numbers in this world? This is actually talking about all numbers in this world where I want to, I want to go from negative infinity to positive infinity. Automatically, I'm talking about real numbers. That's what I mean in equation 9. So all what I'm just trying to tell you now, you need to understand them. Because if you really want to take a decision that we don't want to regret in this type of the world that we find ourselves in, we basically need to understand different types of intervals a random variable S can actually, be located in. Okay, so that's what I wanted to take note right now. Okay, so we've just discussed interval, different kind of intervals. Now we want to move to functions. Okay, we basically want to move to functions. And you know what? When we talk about functions, we basically want to talk about rule, where for each point in one set that we actually call domain. Okay, I'm gonna write something now. Okay, we basically gonna have domain. Okay, and we also going to have what we call a codomain. Okay, and you know what? We got some values right here. Probably if I say x1, x2, x3 until I get to xn, which happens to be random variables, right? I basically want to map from domain to codomain. If I really want to map from domain to codomain, I'm basically need a function to do that. Okay, which are basically going to call a function of x. Okay, I know in your high school you've learned something, you've had something that called a linear function. Okay, for instance, I'm going to give you an example right now. If y equal to g of x and it's probably equal to x plus 1. Okay, now when you take a look at x plus 1 right now, it means if I have any values of x, I will be able to determine y. Okay, which is going to be the codomain. But before I can do that, I need a function to be able to do that. So what I'm trying to present to you right now is that we actually use functions as mappings or transformation. And because of that, we basically are going to say we denote the function by f, or we can simply say we can say f of x. What do we mean by that? Because we actually want to use function as a rule, and that we actually map a point in x, okay, in the domain that we are considering, to values of f of x. What am I talking about here? Let us relate to real life practical situation now. Okay, for instance, if I call x, probably the numbers of hours, worked, okay, on the job, okay, and of course, if I call y, okay, probably the numbers of amount you get paid, okay, amounts paid, okay, amount paid, okay, you know that actually when you work for different hours, of course, you're actually going to get different amount paid. That's what we mean. Okay, so that's what we mean. So it's like you are actually want to map the a given numbers of hours work, okay, to a given amount that will be paid, that a worker will be paid. That's what we mean. Okay, you confirm again if you see hearing me clearly.
I have a question. Is the codomain the same as the range?
Or you said whether codomain mean the same thing as the range, right? Is that your question?
Yes.
You are right. You are right, because the codomain is more or less like like an outcome variable, and of course the range that you talk about will be the possible will be range of values within the codomain. So you are fantastic. Okay, now that is what we mean by function. And you know what? We got different kind of functions that I'm still going to talk about. But take a look at what I have here. Mapping from X to Y. It's like mapping. I wanted to, the way I understand my mathematics, the way I understand statistics, I like relating to real life. I want you to relate to real life. What is it? When I say X, what do I mean? When I say Y, what do I mean? Okay, X, I just gave an example right now. X, probably the numbers of hours worked. Okay, the numbers of hours you work on a job, and Y, the amount you get paid. Different workers actually work for different numbers of hours, and they actually have different amount pay, different, you know what I mean? Now we actually need a function to be able to do that, and that is what we're trying to write here is more or less like a mathematical representation of the way the function work. Okay, you actually need a function to be able to map from an input to an output. That's exactly what I mean. Okay, math is easy, okay, when you relate. Okay, now I want to walk you through different kind of functions that we have. At time we could have a quadratic function. Take a look at this. If I actually have x and I have f of x, okay, but you know what? My f of x is x squared, and maybe probably this is like -1, 0, 1. Okay, when I square that, I'm actually going to have 1, 0, 1. Take a look at that. So what I'm trying to say right now, this guy here is a domain. Okay, that is a domain. And this guy here now acts as a codomain. And you know what kind of functions am I using to map from that to that? Of course, my function I'm using is square in this case. Okay, we can have different kind of functions that will be given. You get what I mean? Okay. Another thing I just wanted to, I'm going to give you an example right now. We find ourselves in a world, I told you the other time, we live in a stochastic environment. In the environment we live in, we basically, the random variable s can assume certain values. Now take a look at this guy now. What am I trying to say? My random variable x, okay, my random variable x is assuming 1, 2, 3, 4. I'm assuming that. And do you not know what the f of s that we have here now? The f of s that we have is just trying to tell us how many times, because when you add one, if you add the random variable together here, 1 plus 2 plus 3 plus 4, what does that give? That will actually give you 10, right? Okay, and you know what we normally observe in this world, like when events are repeated, the question now is, what is the numbers of times that we can actually have one? What is the numbers of time we can actually have two? What is the numbers of time we can actually have three? What is the numbers of time we can actually have four? Now, what you are trying to see right now, it means one occur, 1 out of 10. Okay, you know where the 10 come from? The 10 is just the addition of 1 plus 2 to 3 to 4, which is the sum of the random variable. You get what I mean? And of course, what I'm trying to tell you now, the f of s that you are trying to see here, it means for every outcome, if an outcome is 1, what we're trying to tell is this: if an outcome is 1, then there exists a function for that, okay, which is 1 over 10. When a variable, an outcome variable is 2, it is 2 over 10. When it is 3, it's 3 over 10. When it is 4, it's 4 over 10. Now, what you're trying to see now, we are trying to say that if the domain is a small finite set, we can actually give a table. This is a table now. Okay, and not only that, I'm going to give you another example where we can actually map, a set to any set. Here now, marking red to tomato. Okay, marking orange, mapping orange to orange, yellow to lemon. Look at that, so like that. So what am I trying to give you right now? Trying to actually give you the way we map with function, where we can actually map on the final set, or we can also map, from any set to any set. Take a look at that. Okay, now the next thing I actually, I told you something the other time that we can have different kind of function. Take a look at this guy the other time. I was talking about s squared, but right now talking about the square root of x. Okay, that could be a function, but there's something I want you to say when I'm talking about the square root of s. Then I can't just, s can be all numbers in real numbers. You know what I mean? S can be that. You know the meaning of this guy? Not from. That's what it means. Okay. Now, what I'm going to say now, if I want to get a domain for this, it has to be positive numbers. Look at that. So this guy actually means this guy means non-negative. Can somebody tell me for extra credit, why is it that it has to be non-negative for this function to operate? Can somebody
You
tell me?
can't take the
Any
square root of a
complex
negative number.
numbers then?
It would be an imaginary number.
Yeah.
Okay, I think I've had about 4 people that talk at the same time. Oh my God, you guys are fantastic. Now, those people that talk right now should send a message to me for extra credit. You guys are really smart. Good job. Okay, so because when you find the square root of a negative number, it doesn't it's going to give you an error that will be indeterminate, and that is the reason why we're trying to say, okay, the only condition under this function is going to operate or exist is when the s is non-negative. That is what we mean. You can now say it means this function is not defined forever. This function is defined only if this condition holds. Good job. Okay, now we actually want to go, or we're still on functions, but right now, I want to, what if in a situation where the function is exponential in nature? I know, take a look at this. That's a real numbers, right? All numbers in this world, right? Now, if I take the exponential, like for instance, if I want to do exponential raised to the power 5, or I do exponential raised to the power -5, or I do exponential raised to the power 0, you can use your calculator right now. When you try to find the exponential raised to the power any number, is basically what you're going to get will be between 0 and infinity. You can try that. Anywhere in the world, when you do the exponential of a number, you can never get negative. I'm going to say that again. Anywhere in the world, take any numbers, do the exponential of that. The values you're actually going to get has to be within between 0 and infinity. You can't have a negative. That's all we mean. Okay, that is what this guy is actually talking about. So which means the function that I'm actually using here is an exponential function. Okay, that is what we mean by that. Okay, and that's what I'm actually explaining right here. So which means x is going to be domain, and the exponential raised to power s is actually going to be codomain, which is the function that you need to generate values into the codomain. Take a look at that. We are placing a bound. We have actually investigated that, and the end result can never be negative. You can try that. Okay, now what if in a situation where I basically want to reverse? Look at that. Oh my God, I want to reverse now. I want to take the log. Okay, if I want to take the log, okay, I have to limit taking the log to 0 and infinity, because when you take the log of negative, that will be indeterminate. I just wanted to take note of that. I'm going to say that again. Take a look at this. If I want to take the log, okay, I want to take the log of a variable, which I call the log s. Okay, then I have to use the values within 0 and infinity. Okay, I cannot take the log of negative. Okay, the log of negative is basically going to be indeterminate, and that is the reason why you can't do that. And you know what? Oh my God, take a look at this guy here and this guy here. It's like this guy here is an inverse of that. Look at that. Because you know why? When I have real numbers or numbers in this world, and I take the exponential of that, okay, the result I'm actually going to get is going to fall within 0 and infinity. But what if in a situation where I'm no longer interested in the exponential right now? I want to take the log of a number between 0 and infinity. That will return you back to real numbers. When you take the log of a values between 0 and infinity, you are actually going to get any of the numbers in this world. You could get it negative, you could get it 0, you could get whatever. So, and what we're trying to say is that this log, we actually call that a logarithmic function. Why this guy here, we call that an exponential function. But do you know the takeaway from here? Okay, the logarithmic function is an inverse of exponential function. And y exponential function is an inverse of a logarithmic function. So which means, and that was why I said the two of them, the functions are inverses of each other. This has been mathematically proved. Okay, so take a look at that. So because of that, there's actually going to be a general statement. Take a look at that. Look at this guy here. When I have an exponential raised to power, for instance, I have exponential raised to power 5, and I take the log of that. Okay, when I take the log of that, because the log that I'm taking is to base of e, is to the base of the exponential. Okay, on the normal sense, I'm going to have an e here. And mathematically, this can be written as 5 log e, you know that, right? And what is a log e? That's 1, right? So it's going to be 5. So this is more or less going to be 5 times 1, which is going to be 5. Look at that. And that was why we said, generally speaking, the log, okay, of exponential raised to power x, okay, is basically going to be x. Well, that's exactly what we're trying to say right here. And you know what? When I have a log of x and I take the exponential, that is also going to return x. So what are we talking about? Then what we're talking about is the log of ESP of x, okay, it's also going to be equal to ESP, okay, the log of x, because they both going to return x. Okay, I just wanted to take note of that. Okay, that is the way that is ready. Okay, good job. That is the way that is done. Okay, I think I just and in this course, when I'm talking about log, I'm not talking about the log to base 10. I'm talking about the log to the base e. I just wanted to take note of that. Before I move on, is there anyone in this class who is actually having difficulty with my accent, or is not getting what I'm saying at all? Is there anyone? If you are comfortable, like if you are really getting the information I'm passing across right now, and if you can hear me clearly, okay, I need you to say yes, or you comment yes. Okay, one person. Oh, okay, somebody say you're doing great. Okay, thank you so much. But you know what? If you don't understand what I'm saying, if you don't get what I'm saying, I need you to actually, do not hide your feelings. You know why? You pay for this service, you deserve to be served better. Okay, now I'm gonna go to the next page now. I want to continue with different type of functions. And, on this page, what I want to introduce to you. I want to introduce what we call a constant function, an identity function. Okay, what do we mean by, I'm going to start with the constant function. Take a look at this. Oh my God, what do I mean by constant function? By constant function, we actually mean irrespective of your input, the output is the same. Okay, I'm going to draw something now. Okay, domain, maybe I have 1, 2, 3, 4, and I have a codomain. Okay, and maybe this guy actually give 3. Okay, and this give that give that, all of them give the same. That's a constant function. Okay, which means for every irrespective of the values of x, irrespective of the values of input, the output remain the same. That's what we mean by constant function. Okay, at times we could have constant function. Okay, and you know what, for the constant function, if you want to plot that, let's say you want to plot, right, probably this is y and this is x, and you have 1, 2, 3, 4. Okay, what I demonstrated here, this is like x, this is like y. Okay, maybe this is guy is 3 here, then it means I'm actually going to have that. Look at that. I'm actually going to have an horizontal line. When the values of x is increasing from 1 to 2 to 3 to 4, the values of y remain the same. That's what we mean by constant function. Now, that is what I mean here, mapping from X to C, where C is actually constant. Okay, another function I want to talk about is what we call identity. Okay, identity function. Or what do I mean by identity function? By identity function, we actually mean the values of the input and the output is the same. Oh my God. Oh my God. Look at that. Look at that. I'm actually mapping from X to X. I'm going to give you an example right now. Okay. Um, I got this guy here, 1, 2, 3, 4, and I got a Y. Okay. And one actually map to 1, 2, map to 2, 3, map to 3, 4, map to 4. Then the function that we're actually going to be using here, okay, we are if you want to map that particular function, the f of s is actually going to say we're going to have s to be equal to y. Okay, you're going to have your f of s, it means x and y are the same. That is a situation where you can actually have that condition. When you plot now maybe y against x, I'm going to plot 1 against 1. I'm going to plot 2 against 2. Automatically, I'm actually going to have a perfect horizontal a diagonal line. Okay, that's an example of in fact, this is going to start from here, from 0, which is more or less like a 45-degree angle. Okay, so 1 to 1, 2 to 2, 3 to 3, 4 to 4. That is what we mean by identity function. Because why? If you really want to understand the world, if you want to take a decision that we are not going to regret, we basically need to go statistical. And when you are going statistical, in statistics, we use the knowledge of mathematics. Okay, so and that is why we can, we live in this world mathematically. Okay, we live in the world mathematically. Somebody was talking about give me one discussion. Somebody said it's identity function, basically a bijective function. But you know what, I understand what you mean. I don't want to, you are very close, you are right, but I don't want to use more rigorous nomenclature in this course, so that I don't want to scare my student. I don't want to scare student. You get what I mean? Okay. Okay. So I think I just introduce you to different kind of functions we have, that we can actually play around with. I remember I walk you through a constant function, an identity function, the square function, the square root function. So take note of that. We got different kind of functions that we have. Okay, so I think the next agenda for today is basically probability models. But before I go into probability models, is there anyone who need clarification on what I've presented? Is there anyone? If you are enjoying my party, I'm going to call this statistical party. If you're enjoying my party, I need you to say yes, or you comment yes. Are you enjoying this party at all?
Loving the party.
Okay, thank you so much. Thank you for enjoying my party. Now we want to go into probability models. Now, I think I need to all four of us ask ourselves questions. Why are we dealing with the probability models? Of course, I told you the other time, we live in a stochastic environment. We live in a probability space. And you know what? If we really want to have control over our environment, of course, we need to be able to understand some basic probability models. You remember on Monday, I actually said, what we're trying to do in statistics, we are trying to model reality. I'm going to say that again. What we're trying to do is to model reality. Okay, that's what we're trying to do. Okay, we want to model reality. Okay, because we are modeling realities more or less like, trying to represent, reality, in terms of mathematical expression. Okay, that is what we're trying to do. Now, what we want to do now, I basically want to walk you through probability models. And what do we mean by probability models? Probability model is actually the mathematical representation of random phenomena. I'm going to write that down. Okay, mathematical representation representation of random phenomenon. That's what we mean. Phenomenal. Okay, that's what we mean by probability models. Okay, and you know what? We also call it probability distribution. Okay, and you know, we use this in probability theory. Let me tell you this. If you what in statistics, in statistics, we use probability theory. Okay, and that is the difference between statistics and mathematics, because in statistical models, we actually, the model incorporates uncertainty. I'm going to say that again. Statistical model incorporates uncertainty. Okay, and when I say uncertainty, of course, it means we are actually acknowledging the fact that when we're trying to model reality, our model cannot give exact reality. I'm going to say that again. We're making attempts to model reality, but I want to tell you, model is not the same as reality. But you know what? Model is an approximate reality. Is an approximate reality. You know why? Model is an approximate reality because in any statistical model, we actually incorporate the random component. Statistical models are not deterministic. Okay? The reason why statistical model are not deterministic is because of the fact that there's a random component that we call probability, component. Okay, so because of that, model cannot give us exact reality. Our attempt is actually to have what I call an approximate, reality. That's what we mean. Okay, now, because of that, we basically, I said probability models is actually called probability distribution. Okay, now what we mean by probability distribution, on Monday, I introduced you to sample space, right? I introduced you to experiment. In this world, we experiment. You don't need to be in a physics lab. You don't need to be in a biology lab before you can experiment. Whatever we do that generates an outcome, we are experimenting. It means we are experimenting. Now, the possible, outcome that we can have in an experiment is what we call sample space. Okay. Now, when I want to talk about the component of probability models now, when I want to talk about the component of probability distribution, so what I'm going to say, it is described by its sample space, events within the sample space, so number one, sample space, events within the sample space, and the probabilities and probabilities of events, okay, within the sample space. I'm going to say this again. When we're talking about probability distribution, okay, it is actually defined by a sample space. Every probability distribution must have a sample space. And you know what I mean by sample space? Collection of possibilities. And don't forget, within the sample space, we got events that we call family of events. Okay, within the sample space. And you know what? Every event within the sample space has their corresponding probability. What are we trying to say? When you experiment, okay, and you have an outcome is an event within the sample space, and every outcome has probability. Okay, every outcome in this world, like for instance, when you are into business, okay, you know, I told you yesterday, the sample space of a businessman or a businesswoman is actually profit and loss, right? Okay, those are events, those are outcomes within the sample space. But let me tell you, profit as an event within the sample space has a probability. Okay, loss as an event within the sample space has its own probability. Okay, if you know, for every event there exists probability associated with it. That is exactly what we're trying to say now. Okay, now we have the probability models that we're talking about. We have several ways that they can be specified. Okay, we can use probability mass function, which we're still going to talk about extensively in this course. Okay, the probability mass function, the probability density function. You know, the probability mass function is a probability for discrete, discrete random variable. You know, yesterday I actually walk you through different types of random variable. We got a discrete, we got a continuous, and the probability density function is for continuous. Okay, I just wanted to take note of that. We're still going to talk about them, okay? Then we have a distribution function. We have a probability measure. We have expectation operator. I'm actually going to tell you the meaning of each of these. You know, we are still going to talk about each of these extensively in this course. But what I'm just trying to show you now is just like, okay, these are ways to specify probability models. Okay, now I want to start with the probability mass function now. You know, I told you when you look at what I have here, you know, these are ways to specify probability models. But right now, we're to focus on this guy now. Okay. And when we're focusing on this guy, we basically, you know, trying to study probability associated with discrete random variable. You remember yesterday when I was talking about discrete random variable, where we are, you know, the discrete random variable is, you know, a variable that can be expressed as a whole number. Of course, you know, yesterday when I was walking you through sets, I actually gave you an example of whole numbers, right? We're talking where whole numbers start from 0, 0, 1, 2, 3, 4, 5, 6. Those are whole numbers. Okay. Okay, go ahead.
When we say that the probability mass function is for discrete random variables, does that
Yeah.
mean that x is discrete, or does that mean that f of x is discrete?
Oh my God, that's a very good question. Look at me. You've asked a very, very good question. If I hear you clearly, you said, if we say the probability mass function is for discrete random variable, are we trying to say S is discrete or the f of S is discrete? Okay, it is X that is discrete. Have I answered your question now?
Yes, thank you.
Okay, you're welcome. So S is discrete. Okay, so the probability mass function means the probability function for discrete random variable. Okay, now and that is why what we're trying to say right now is from a sample space. Okay, you know, yesterday I actually I told you we're basically going to use this for sample space. Okay, so for sample space, and you have a function, we're going to be mapping into the real numbers, and of course the f for discrete random variable, the f of s has to be greater or equal to 0, because it's a probability where s less than that, and when I sum the probability together, it must be equal to 1. Okay, I just wanted to take note of that. Now, this is what, you know, I was telling you the other time, if I have x1 up to xn, each of these, s1 has its own probability, s2 has its own probability. That's exactly what we mean. And you know what? When we add all of that together, it's basically going to be equal to 1. That's exactly what we mean. Okay. Now, I wanted to take note of that now. So the takeaway from here, these are just elementary. Yeah, the takeaway from here is just like, okay, when I have event outcome, I have a probability associated with the outcome. Okay, that is the takeaway. That's what this guy is trying to say. And you know what? If I have x1, the probability is actually going to be, the function is going to be g of x1. And that probability have to be greater or equal to 0. It has to be positive. It has to be non-negative. And in such a way that if I have a g of x1, g of x2, until I get to g of xn, when I add them up, it must be equal to 1. Okay, that is what we mean. Now, I'm going to walk you through an example now. I'm going to stop my share. Before I go, I'm actually going to stop my share and I'm going to walk you through an example right now. Give me 1 second. For instance, if I need you to confirm if you see my whiteboard. Are you confirmed? Can you see my whiteboard? Is everyone see my whiteboard?
We can't see it.
Oh, you can see it. Thank you so much for confirming that.
I said
Now,
we can't. I can't see
oh,
it.
you can't see that, right? Oh, okay.
No.
Give me 1
Say
second.
you started the screen sharing, but we can't see a whiteboard.
Oh, okay. I'm gonna do that again. Yeah. What about? Okay. Let me just give me 1 second. I think it's kind of, I'm gonna stop this share now. And multiple. Okay. Now, what about? Give me 1 second. Let's see. Can you see my whiteboard now?
Yes.
Thank you so much. Now, what I basically want to do now, I want to walk you through an example before I go, and you're gonna love the example. Now, example now. I'm going to use additional 3 minutes, but if you have other lecture, you can log out. This is being recorded, okay? This is being recorded. Now, I chose a fair coin twice, okay? And let x be defined, okay, as the number of heads, okay, I observe, the number of heads I observe. Find the range of heads, okay, which is this guy here, as well as its probability mass function. You know, we just deal with the probability mass function now, right? The one we call PMF. Okay. Now you are given this question. You can screenshot that. I quickly want to show you how to solve this now. Okay. This is more or less like an exercise. Like I said, for those of you who have other lecture, you can log out. If you want to log out, this is being recorded. You can have the opportunity to watch the video later. Okay, now you toss a fair coin twice. Let X be defined as the numbers of X. You know, in a coin, in a fair coin, you have head and tail, right? Okay, you have head and tail, right? Okay, now you now want to define what is. You actually, you use X to define the numbers of X you observe, and you want to find the range of X. Okay, now if you want to do this, you need to perform the experiments. Okay, now you want to perform the experiment now. You're tossing a fair coin twice. You will need to look at the possibility. Look at that. Head, tail. You're going to start with that. Can you use a tree diagram where head goes to tail and head goes to tail? Now, if I want to write the sample space now, it's going to be head, head, right? Head, tail, okay? Tail, head, and tail, tail. Now, this is my sample space. Now, if this is my sample space, don't forget, the X represent the numbers of X. The numbers of X, okay? That, I said the numbers of X. The numbers of X, if you look at this arrangement now, could be 0, 1, 2. You know why? This is where we have a tail and tail. Head, it means head equal to 0. It could be 1, it could be 2, where you have head and head. So it means the range of X is basically 0, 1, 2. This is the range of X because we're talking about the numbers of X. Now, you now want to find the PMF now, which is the probability mass function. Okay, you want to find the probability of X, okay, given K, which is, you want to find the probability of S equal to K. Here your K can be 0, can be 1, can be 2. Don't forget. Now, if I want to find the probability, for instance, of S equal to 0, what do I mean? S equal to 0 means no head. How many? Look at that. Tail is 1 out of 1, 2, 3, 4. That will be 1 over 4. You see that? What about the probability of S equal to 1? S equal to 1 is basically talking about how many times can I see one head? Look at that in the arrangement. This is 1, 2, which is going to be 2 out of 4. When you reduce that, that will be 1 out of 2. Now, what about the probability of S equal to 2? Okay, that is, how many times can I have 2 heads? It's right here, which is 1 out of what? 1 out of 4. I'm done. Look at that. It means for any given random variable X, we are able to determine the corresponding probability. So take a look at that. Okay, this is where I'm actually going to stop today. We are done with this material. We're going to start a new material tomorrow. Before I go today, is there anyone want to ask a question? Is there anyone who need clarification on anything before I go? Okay, in the absence of question, make sure you stay safe, okay, and have a very, very lovely day. I'm going to see you tomorrow. So bye for now, everyone.
Thank you.
Thank
Thank you.
You're welcome.